Hi everybody. Today we are going to finish our discussion of distance measuring, and we are especially going to focus on the total station. So in the blog today, those of you who are in engineering surveying will refer to Chapter 6 of your textbook. Those of you who are in practical surveying will refer to Chapter 3. So as we go through the information for distance measuring, the first thing that we see is we have just some different instruments that we use for chaining or for using a steel tape. And these are things that you're familiar with. This just refers to a range pull. We have some chaining pins. We have the tape itself, whether it's a steel tape or just a standard measuring tape, and plumb bobs. This slide just refreshes your memory on how you use a cut tape or an add tape, where the gradations are at one end of the tape, and you either add or subtract the number that you read on the end to the forward chain man's reading in full feet or meters, or tenths of meters, depending on how the tape is graded out. So this is a process referred to as breaking tape. This is how you measure a horizontal distance on a slope. Now, in our last vlog, we had talked about measuring a slope distance and correcting it to a horizontal distance, which I think is somewhat preferable, but sometimes this can be handy as well. So once again, just the idea of breaking tape in order to get horizontal distances. So another way to compute, this is what we had talked about in the last blog, where we have some sort of a horizontal distance h and a vertical distance d, and we can use a little bit of trigonometry to find the slope distance, or to find the horizontal distance or the vertical distance, because they are all intimately related to each other via that angle of elevation. Now, this is a diagram of the idea of sag, which we talked about, that catenary that gets formed when you pull a tape, and why you have to compute sag for every time you pull a tape. In other words, if you have a 300-foot pull, your sag is going to look tremendously larger than if you have a 100-foot pull. And so it doesn't add together. It's actually based on the length that you pull times itself 3 times. So length times length times length. So you need to compute that catenary based on the length that you actually pull rather than the total length of the measurement. So one of the things that we start to talk about then is a total station. And total station measures in a completely different way. The distance that's measured by a total station is equal to some full number of wavelengths plus some partial wavelength that returns to the total station after it hits the prism, divided by 2. So in other words, you set up a total station instrument. It sends out a series of light waves, bounces off the prism, and returns. Now, it is a common mistake that people make, that they think that you can measure this like we do in statics or physics or even in algebra, where a distance is equal to a rate times a time. The problem with this is that the light waves that are sent out from a total station travel at the speed of light, which is incredibly, incredibly fast. So that means that the time for it to return is incredibly fast. And you would need to have a super accurate clock that really doesn't exist in this universe in order to measure 1/100th of a foot, which is the level of accuracy that we're looking for with survey quality instruments. So what a total station actually does is send out several different wavelengths of light. None of these are visible light, of course. And then it measures actually what the phase angle is right here when the wave returns. And what that tells it is that the total distance between the prism and the total station is going to be some full number of wavelengths plus one partial wavelength that can be determined based on this phase angle. Now, obviously, for one light wave, one wavelength, there would be an infinite number of solutions to that. However, statistically speaking, if you send out approximately 7 different light wavelengths, you will come up with one unique solution, or sometimes 2 unique solutions that would satisfy all of those equations. And that's actually what the computer in the total station does. So it bases it not on distance is equal to rate times time, but rather on distance is equal to some full number of wavelengths plus this single partial wavelength, and it does that 7 different times. So the distance is going to equal n, some n, 1 times lambda 1 times this partial times lambda 1, 2, and so forth, until there is a unique solution that's arrived at. Now, once in a great while on the total station, you will get 2 possible readings, and it will give you 2 numbers. It might say 26.41, comma, 267.42, or something like that. Now, when it does that, what it means is your total station has found 2 mathematical solutions that are equally possible mathematically. However, if you look at the distance, there's only going to be one of them that makes any sense. So you don't average those 2 numbers together. One of them is correct. One of them is a solution. The other is not a solution. And you have to kind of look and decide which one appears to be correct. And that's the one that you choose. Right? So this is a picture of what they refer to as EDM. EDM just stands for electronic distance measuring, and that is, for us, the total station. Now, intermediary to workable total stations and basic theodolites, there were instruments that were only electronic distance measuring, so you could use them in conjunction with a theodolite to get angles and distances. But the process is still the same. Lambda, this symbol here, is the same as here. It refers to the wavelength, so that this is half of a wavelength, this is the other half. So from the beginning through the first half through the second half, that is just a full wavelength. But basically, this is what we're saying is you have this wavelength goes to the reflector, bounces off the reflector or the prism, and returns to the total station. Then that mathematical reduction is done, and a unique or 1 or 2 unique numbers are determined. If you have one number, you know that that is the length. If you have 2 numbers, you have to decide which one is the length. All right. So this is just another example of this P, or that partial wavelength, the phase angle that returns, not the phase angle, but the fraction of the wavelength that returns to the EDM. So we go out the length, and then we come back the length, and we measure that phase angle, or we measure that partial, in order to get the solution to how far distant is the total station from the reflector. All right, so this is just a little bit more about the mathematical functioning and the mechanical and electrical functioning of the total station. This is a picture of a series of 3 prisms. We use a single prism in both cases, and a picture of a total station. This is similar to the one that we have, the more modern one, the Leica. We also have a Sakia total station, and we've looked at both of those. Now, this type of a total station, this isn't really total station, this is a laser measuring tool that people can use, like real estate agents will use them to determine square footage of rooms or houses. Contractors will sometimes use them to determine distances for construction materials and so forth. Neither one of them, this type of instrument is not suitable for surveying distances and the precision and the accuracy that we need. but it's another example of how the technology is used. And you don't use a prism with this, it just reflects off something that it hits. So you have to be careful of interference as well. That can happen with a total station as well, but we'll try not to. You always want to make sure you're actually shooting the prism and not something that got in the way, or missing the prism and getting some other type of a reading from some random object. Now, this just refers to how we can compute an elevation difference or a slope distance using, once again, total station and prism. This is a sideways view of the prism. You can see we have this plummet line, and we have the wave going from the EDM to the prism, reflecting and going back to the EDM. The effective center is back here. There are depth readings for a prism and constants, this K value of a prism. Now, if you use a total station that is not designed to work with a particular prism, you can use the configuration settings on your total station to correct for this, because obviously the deeper the prism is, there's going to be a little bit of a constant that needs to be taken into account. I was going to say error, but it's not really an error. It's more just a correction that you need to make. So when you have a total station on a prism, you have to make sure that the prism is set up so that the K value is the same as the K value for the prism. So generally speaking, the prisms are stamped or have stickers on them that tell you what the constant is, or you can look up the manufacturer and see what the constant would be, and then you can use that value in order to get ultra precise distances between the prism and the total station. Now, we just got through working with steel tapes, and we talked about the corrections that you need to make for steel tape. We had a temperature correction, a pull correction or tension correction, a sag or catenary connection, and a slope correction. When you use a total station, because it's a light wave, there's going to be a little bit of a pressure error and a temperature error. So basically what we're talking about is on the left hand side here, this would be the parts per million of distance error based upon this line, which is temperature, and this line, which is pressure. So you have to go to the top to find how many degrees off you are on temperature. So if it's 5 degrees, you come down here, you come over here, and that's going to be the distance error. You're going to have about an 8 part per million error based on temp, or based on temperature goes to here, sorry. Let's go here to here. So there you go. So you're going to have about a 7 part per million temperature correction. Positive pressure, on the other hand, in millimeters of mercury, standard atmospheric pressure is about 760 millimeters of mercury. So if you are not any off from that, you would have no correction. But if you're 25 millimeters of mercury below, you're having a low pressure front, you're going to have a pressure error of about 9 or 9.5 parts per million. So you have to take those into account as well. And that becomes precise, obviously. A part per million means that you would be off 1 foot in 1,000,000 feet. Or if you take 1,000,000 feet, let's work inside my calculator, and you divide it by 5,280, that is 190 miles nearly. So that means that you would be off 1 part per million is a foot in almost 200 miles. So that's quite small. But if you're measuring very long distances, or you need things to be extremely precise, you need to be careful to take into account those measurements. All right, so this is the end of our blog for April 12th, which is a Thursday. I have posted the homework. I will not be posting notes. I think that the PowerPoints and the reading in the book are fairly complete. So you have a homework assignment posted for this. And after we are done with this homework on Thursday, we will concentrate the rest of the semester on the Public Land Survey System and how that applies to legal descriptions. So talk to you later for our next vlog, which would be for the 17th of April.